Thank you. First of all, I would like to thank the organizers for inviting me to this wonderful conference, summer school, and also to this very nice place. So today I'm going to talk about this numerical method for ground states of spinor BCs. So I noticed that the talks basically on the single GP, the scalar case, so no spinor yet. I hope that in the future you will consider doing this spinor superfluids. So this is the outline of my talk. So before move to the numerical methods for the spinor case, so I will give some review and introduction to the single component case, and one of the main method we are using is this green flow type method, but with some simple modification by a Lagrange multiplier. And then we will move to the multi-component pseudo spin half case, and then the spin one case, and then general spinor case. So this BC is quite standard. So we have seen quite a lot in the previous talks. And what I'm interested is the mathematical model here. Of course, we have this. So this is a quantum embodied problem. So we can describe it by this linear Schrödinger equation, but with very high dimensions. But for the simplest description, we can use this mean field approximation. We have this GP equation. So the dimension is much lower, and but then we pay the price of nonlinearity here. So this derivation has been shown previously in Ricard's talk, and so here we basically this is the embodied Hamiltonian, and here we only include the binary interactions between the particles, and then we have this. So they are in the BC state, so they can describe by this single wave function, and we have this simple approximation to the interatomic potential. And finally, we will end up with this GP energy functional that we are going to study. So we work with this simple GP equation. And here we write the equation in this rescaled form, so all the units are equal to 1, something like this. And then we have, so for the system, of course, Y is the mass constraints, which and the other one is the energy. Okay. And the two fundamental problems in this case is Y is to compute the ground state, so which is relevant to in the experiments because it's the temperature is low, so the system is in the ground state, so that's more relevant for our purpose. We can view it as energy minimization problem under the constraint that the total number of the particle is fixed. So this non-convex minimization problem. The other one, then we can. The other one is to compute the dynamics, basically to simulate how the system evolve. But here in this talk we focus on the ground state problem. So to solve the ground state, so this can be also viewed as this nonlinear eigenvalue problem by looking at the Euler-Lagrange equation to this variational problem. Then we have this chemical potential mu here, and on the constraint that the L2 norm of the wave function is normalized equal to 1. So based on these two approaches, we can classify the numerical methods for computing the ground states. So one is based on this minimization approach. So you just want to minimize some energy functional. The other one is we solve the eigenvalue problem, but you look for certain properties of the wave function or the eigenvalues. So now, so this is a partial list of the existing method for computing ground state based on this minimization idea. So from the normalized green flow or the imaginary time propagation in physics, and also there are some variant, and also a very nice idea. This is Sobolev gradient by Ionut, and also later they introduced the Riemannian optimization approach with Bartek. They have this, and then there are also other things like we have some method now for the grain flow. So there are other approaches, and also recently there are some accelerated method for the first order gradient method from the optimization community. So when you add some second order derivative there, the convergence can be accelerated. So there are also some recent work on this. And also based on the nonlinear eigenvalue solver, because this is a bit similar to the density functional theory in electronic structure computation, but it is much simpler in this case because there is no orthogonal constraints. But you can also solve it in this algebraic way. So you first to discretize then some algebraic eigenvalue problem then without using the minimization characterization of the ground states. So our talk will be based on this imaginary time propagation, or this normalized grain flow approach. So let's review what's the idea of the imaginary time propagation. So the basic idea is that we first propagate the solution in the imaginary time of the GP equation, then do projection to satisfy the constraints. So this was a simple idea. So this the algorithm here proposed by Bandu in 2004. So the idea is basically you do unconstrained minimization, then you do a projection back to satisfy the constraints. So in the linear case, so this is easy to consider, because in the linear case, so the eigenvalues, the solution can be written in this superposition form, and you will see that all the eigenmodes will decrease in time, but only the first one will remain the most. So after you repeat the iteration many times, then eventually only the first one will lie in the final solution. So this is somehow the power, inverse power methods of the eigenvalue solver. Okay, so for the nonlinear case, so though there's no analysis about the convergence, so because the paper only deals with the linear case, but in practice, so this algorithm performs well. And this one can be viewed as first order splitting method for describing this continuous normalized grain flow. So in mathematics, if you want to minimize some energy functional, so one way is to use the grain flow, and you have a constraint, then you add some Lagrange multipliers there to enforce the solution remains on the constraint manifold. So that's the idea of this. This basically the grain flow on the constraint manifold, which is the L2 norm of the wave function is equal to 1. And by using the normalization constraint, we can compute the Lagrange multiplier in terms of the unknown function phi. So this sort of integral differential equation. And because the construction of the grain flow, so the wave function phi is always in the constraint manifold, and the energy, because it's grain flow, so the energy is always decreasing. So continuously, if we evolve the system along this flow, then eventually we will reach some signal points of the energy functional with the constraint. And if we view this one, then the previous projection step is equivalent to solve the Lagrangian part to enforce the L2 constraints. Okay. And another thing is that because once we do use this grain flow methods, then to practically implement it, so we only need to solve the first this imaginary time PDE GPE discretization. So what they propose is that you should use first order backward Euler scheme, but with the nonlinear term to in this explicit implicit form. But then this was discovered by Farrell and in 2018 that only this algorithm will converge in the correct ground state of our purpose. The other one, if we do it fully implicit or fully explicit, the solution converge, but converge to a different state with an error depending on the time step size tau here. Okay, so the thing is that if we consider the grain flow in the continuous level itself, because this one is a nonlinear equation, so if we put the initial state as the ground state itself, because it's nonlinear, then as it evolves, the solution will deviate from the ground state, not in the one-dimensional linear space spanned by the ground state, but it will have some deviations depending on the time step size tau. Then once when you do the projection back, because this projection is simply a scalar of the scalar multiple of the state phi star here. So because of this, then once you follow this nonlinear dynamics, then the solution will never come back exactly as the initial ground states. So that's the reason. That's the reason why this why the algorithm to discretize the PDE in other form will fail to produce accurate solutions. For this one, because this is somehow the nonlinear term is linearized, so this one can be viewed as linearized dynamics. So once we linearize the dynamics, then we start with a ground state, and then the solution will evolve in this y-dimensional linear subspace. Then when we do projection back, then it will give the exact ground states. Okay. So we can look into this further by considering other types of the discretization of the PDE part. So the first one is that we have seen before, to do this one in explicit implicit way, or we do this for the majority part, the linear part to implicitly, and the other part to in explicit way. And this alpha is some stabilization constant to enlarge your time step size. And or we can also do this one in another way, or in the fully implicit way. All this one will followed by the projection step to satisfy the constraints. And we can argue that when it's convergent, so the intermediate and the final step size, and they satisfy this scalar condition. Then we can take it back in the equation and compare it with the Euler Lagrangian equation satisfied by the ground states. And if we have this backward and Euler scheme with explicit implicit treatment, then we find this one can coincide with the Euler Lagrangian equation of the ground states. Okay. But for this one, of course, this is fully to solve a linear implicit equation at each time step. So normally, for the inner iteration, we need to do some either fixed point or other types of the iteration. Okay. And then we can also use this one. So at each time step, we only need to solve a constant coefficient Poisson equation, so can be solved very efficiently. And for this one, if the algorithm converge, Then we find that the Euler Lagrange equation satisfied by this converged state would be like this one, and normally this C cannot be equal to 1, and this one then have some difference between the from the original Euler Lagrange equation, because the original one, this is 1/2 the coefficients. Okay, so for this kind of discretization, then you will see the time step size will have some impact of the error, the final error. Okay. But this is consistent with the numerical PD theory, because once you discretize in space and time, you have error from space and you have error from time. But here, because our aim is to obtain the final ground states, so when to converge, we do not want the error of the time step to play in the final results. But for this kind of discretizations, this order tau error cannot be avoided if the discretization is not done correctly. Then we have this one. And then we come up with a simple modification. So basically, the algorithm fails for different kinds of discretizations for the PD part, because that if you put the initial state as the ground state, so it will deviate from the true ground states. So then we to eliminate this non-zero initial velocity, we just put the explicit Lagrange multiplier back into the grain flow part. Then once we do this one, then if the initial state is chosen as the ground state, then the velocity is equal to 0, then the solution will not move, so it will stay there. That's the idea. And of course, the Lagrange multiplier can be introduced in other way. For example, we can do it in the implicit way. So this can depend on the state variable phi here. But here we just choose to introduce this one as a source term. So so you can change your code in a minimum efforts to solve this one. Okay. Then so the good thing is that for this one now, to describe the grain flow part, you can use any temporal discretization scheme you want to describe the set the PD. So as long as it evolves and converges, then the convergent state will not have error depending on time step tau. So this Lagrange multiplier can be also introduced in other forms. Okay. So this also partially explains. So because in the physics literature, some people they use this splitting method to compute the ground states. But the splitting scheme here, you will see it can never eliminate the error depending on the time step size tau. Because once you split, the dynamics will always be non-linear. So based on the analysis before, if you use splitting method to compute the ground states, then you always have some trouble there. Okay. And this is some simple analysis for the discretization with this Lagrange multiplier. So we compare our results with the previous results derived in 2004 by Bao and Du. So basically, once you add this explicit Lagrange multiplier, then the result is at least good as their results. So nothing to lose if you add this Lagrange multiplier here. So what we usually do is, because now we can choose whatever discretization we want. So we usually do this one. For the kinetic part, we do the implicit way, and for the other term, do it fully explicit, and then we add some stabilization to remove the time step constraints. So once we do this, then at each time step, we only need to solve a constant coefficient Poisson equation, so it can be done very efficiently. Okay, and also we can also because of the Lagrangian multiplier, so we can use any numerical scheme to describe this PDE part. It's okay. And this is some computational results. So the last line is the residual computed by the Lagrangian Euler Lagrangian equation. So this is the method with the backward Euler discretization, but with implicit explicit treatment on the nonlinear term. So you will see. So near results, the residual is consistent with the stopping criteria. And if you describe the PDE in other way, you will see the error will actually depend on the time step size. And if we add the Lagrangian multiplier, then no matter what numerical discretization we use, then we always have very accurate solutions. So you will see actually the chemical potential and the energy does not differ too much. But when we go further to the Bogoliubov the German equation to compute the eigenvalues there, you need to have a very accurate ground state to compute the PDG excitations. So this is for the single component case. Then let's move to the multi-component case to see what should we do if we have multi components and also probably more constraints. What should we do? So first we look at the spin half system. This basically we have two different spinor states of the one atom, and then we have a coupled GP here. So this V1, V2 normally they are the same. These are the confining potentials, and then there are some other parameters. So when this omega is non-zero, that means the two components can interact and can change. So if omega is equal to 0, then there's no there's no mass transfer between the two components. Then the energy and the ground state should be defined in other way. So for this system, in general, when omega is non-zero, then we have the total mass. The mass of the two components is fixed. So we have this total mass equal to 1. Also, the energy per particle is written of this. So when you see in computer ground state, so our first idea is to extend the normalized grain flow in this case, because it's still an energy minimization problem. So it's natural to use this grain flow type technique. Of course, we can also use to compute the solution based on this eigenvalue formation. But here we use this one is basically the same, but we introduce the Lagrangian multiplier into the expression. So we first do the imaginary time propagation, then do the projection. But because in the multi-components, so each component we need one projection constant, but the total here we only have one constraint. So there are some ways to determine the projection constant for these two components. So then again, we view this one as a spin scheme of this continuous normalized grain flow. Then the projection type, the projection scheme can be thought as solving this Lagrangian part, because the Lagrangian multiplier there's only one constraint here, so the Lagrangian multiplier here they are the same. So when we solve this one, the projection constant actually they are the same. So for this one, we have an additional equation to determine these two projection constants. And this is some simple example to show that in the multi-component case, so there could be more rich phase separation phenomenon here. For this one, I think we increase the parameter, this internal Josephson junction effect. So when this omega increases, so they will drive the two components to be the same. And the other one is like, so here we choose this omega delta equal to 0, and we choose it in a box potential. And this interaction constant, they are chosen to be equal to 0. And if in the homogeneous case, when the interaction constant is equal to 0, then when the interaction between the two components they becomes to be positive, then it will drive the two components to be fully separated. But here is that if we consider a box potential, then the kinetic energy will come into play, and will try to suppress the separation of the two phases. So like here 1D, 2D, and 3D, because in the homogeneous case, as long as beta 1, 2 is positive, then the two system will the two components will be fully separated. And this one, when this eta equals to 1, that means phi 1, phi 2 is equal. They are equal. Basically, phi 1, phi 2, they are the same. So they are fully mixing. When this factor is equal to 0, then that means phi 1, phi 2, they are fully separated. And for this one, you will see there's always a critical number, actually depending on the size of the box trap. That up to this positive number, the system will still be fully mixed. And this one is changing the size of the box potential. And this different scenario is basically because of the scaling of the interaction energy and also the kinetic energy in different dimensions. So this figure is actually refers to this one. And for this phenomenon, we actually can give some rigorous mathematical proof based on some PDE estimates. And but the multi-component case can be actually more interesting because you can also consider the fractional vortices in the multi-component case. And then the next we move to the spin 1 case. For the integer spin, so like the spin 1, we have 3 components. Then the GPE can be written in this 3 coupled GP. And here we write here in a compact form. So this H is the single Hamiltonian, and the rho is the total density. PQ are the linear and the quadratic Zeeman effects. And this capital F is the spin vector, and defined by these 3 spin matrices. All right, and then we have the energy can be written in this very compact form. And we can, for this one, because the 3 components, they can transfer mass. So we have the total mass is equal to 1 to be normalized. And we can also add another one called magnetization. It's basically in the Z direction. So the magnetization is a fixed number. So here we can consider the ground state as we fix these 2 constraints and then find the minimization of the energy. Okay, so we can also write down the overall Lagrange equation to look. So this we have we use some symbols to simplify the notations here. And for this system, there's 2 simple reduction. So when the quadratic Zeeman effect is equal to 0, then we have this ferromagnetic case where the spin interaction is negative. Then essentially all the components are the same up to some scaling factor. And the anti-ferromagnetic case is that when the beta 1 is greater than 0, then the zero component must be equal to 0. So the 3-component case can be reduced to a 2-component case. And the classical method is basically we can directly discretize this integral differential equation. But if you want to do it implicitly, then this could be very expensive. And the previous they use this classical grain flow, but our point is that if you want to discretize this equation, then a very special treatment on the temporal discretization has to be chosen. And the projection constant is basically can be, so we have 2 constraints, but we have three components. So we need an additional equation. So this equation can be found by view the projection step as the splitting for the Lagrange multiplier step. So we can determine the third equation to determine all the 3 projection constants. And we one thing we want to emphasize is that in this multi-component case, so if we do not add the Lagrange multiplier, like here we do some classical discretization, this is like explicit implicit way, or this partial implicit partial explicit, or fully explicit. Okay. If we do this one, then usually they will have some accuracy problem due to the time discretization. The problem is that once they converge, then we want this equation to be exactly the Euler Lagrange equation in the original form. So then this will require either this matrix equal to 1 or this P is equal to the identity. But normally, this cannot be satisfied unless in the equation like these 2 Lagrange multiply. So if one of them is equal to 0, then some of this scheme can work. Can be reduced back to the Euler Lagrange equation. But in general, no. And so then to avoid this inaccuracy, then we added the Lagrange multiplier back into the grain flow. For that one, then we can use whatever consistent numerical discretization that we want. Okay. And eventually, when they converge, then the ground state would be exact. And we always use this one in practice because at each step, only a constant coefficient of this Poisson equation to be solved, so can be done very efficient. And this is some numerical comparison. So this for the we pick up some example that the mu and the lambda, the two Lagrange multipliers, and they are both non-zero. So we use different discretization for the PD part and compare the accuracy here. You will see the residual, they always cannot be the same as the stopping criteria. Though the energy and actually the Lagrange multiplier actually is still quite accurate in the end, but the solution vector itself are not accurate enough. Once we add the Lagrange multiplier, you will see the solution vector is also very accurate. Okay. But for the special case, like when we have this one of the Lagrange multiplier equal to 0, basically either we are in the anti-ferromagnetic or the ferromagnetic case. So for this one, one of the Lagrange multiplier is equal to 0. Then we see the previous one. If you do the temporal discretization in an appropriate way, then we have the accuracy of the solution. But if we use the Lagrange multiplier, then no matter what kind of numerical discretization we will use, the solution will always be very nice. Okay. Then the next is we try to extend the discussion to the general spin case. Then so the basic approach, we use this normalized grain flow. So the key steps are first to a grain flow part, and then the next one is to projection to satisfy the constraint. It's basically these two steps. And for the grain flow part, we already know that if we put the Lagrange multiplier into the grain flow equation, so you can describe the grain flow part very flexible. So the only way is the only thing left to do the extension to the general spin case is actually how we determine the projection constants. Okay. So here we take an example of spin 2. For the spin 2 case, so then we have these 5 components. So to determine 5 projection constants by only 2 constraints. So the basic idea is that to view the projection as the splitting to solve this ODE. This ODE has 2 parameters, 2 Lagrange multiplier corresponding to the constraints. So then we can solve it exactly in the exponential form. So then the Lagrange multiplier should be in this case you only have 2 free parameters. Then when we plug in, then we need to solve this algebraic equation to find the projection constant. And for the spin 2, then this one would be a quartic equation. Then the other is that because the algorithm is actually sort of first order splitting for the original continuous grain flow, so the projection can be done in an approximate way. So we can solve this one with some error to be exactly the exponential form. So when this delta t is small, so we can approximate in a first order way by this Taylor expansion. So if we do this one, then we find a quadratic equation. But this cannot be guaranteed to have positive roots. Okay. That's the problem. But in practice, this can always be done when the convergence is near. The last one is actually we can do the Taylor expansion. We can play the trick here in a different way, like in the denominator. For this one, spin 2 is an octic equation. But this one, good thing is that positive roots can be guaranteed, because if we think the projection is done by the optimal L2 projection to the constraint manifold, then the equation for the projection, they are 2 Lagrange multipliers will be exactly the same as the equation we obtained here. So of course we can, based on this idea, we can actually develop more and more projection strategies. Okay. So now we have both normal grain flow and also the projection. So we can now do any composite case as we want. But for the last thing is we want to say there is a benefit if we put the Lagrange multiplier into the grain flow part. So before what we do is always do the exact projection onto the constraint manifold. Our starting point is here. So once we have this multi-component case and we follow the Lagrange multiplier modification of the grain flow. So because previously we do the exact projection, but here we see if we have this one, then actually we can use inexact projections. Okay. So the basic idea is that the continuous flow will lead us to the correct ground state of the problem. Somehow when we do discretization, so it will deviate from the solution manifold of this equation. So of course you can always project back the solution exactly on the solution manifold. But because the manifold itself, the PD itself has some corrections, so if you do the projection to let the solution deviation from the constraint manifold, not to keep it small, so the grain flow mechanism will automatically pull it back to the constraint manifold. So that's our idea to improve the projection parts. Okay. So in this case, the projection constant from the Lagrange multiplier can be also solved by solving this ODE and in this type. But because we have some, we put the majority part of the Lagrange multiplier in the grain flow. So in the projection part, so this C0C1 is actually of higher order in tau. It's actually of order tau square. So from here, then we see we do Taylor expansion, and this one is a much higher order which we can ignore. So then when we plug in, then we just use this leading part to construct the two equation, and we will immediately find this actually 2x2 linear system, and can be solved analytically. And this quantity is actually, so as long as at least two components are non-zero, so this denominator is non-zero. So you will see these constants are well defined and are explicitly given here. And we plug in back, then we get a positive projection constants. But the price is that now, because this is approximation to the exponential, so they are not so after doing the projection, so the constraints are not exactly to satisfy. Okay. And then we can do some simple analysis. So this before we do projection, this is after we do projection. So they are we will find so this is of the square of the deviation here. So we will see, though we cannot prove it in a very rigorous way, but here can partially explain. So as long as the deviation of the two mass and the magnetism is small, then once you do the projection, then it will become much smaller. Okay, so this has a mechanism to remove the effects of the inexact projections, and the grain flow will automatically correct the constraints. So this is the first type inexact projection. On the other hand, we can also fix one. We can exactly specify one, and then the other one have some relaxation. So here we enforce the total mass constraints, and then we only left with one parameter to be determined. And for this one, then again we use this Taylor expansion to find the approximate projection constant. So we can, this one can be also solved analytically. But the bad thing is that we cannot guarantee this projection constant is positive. And but the good thing is that at least one constraint is exact satisfied. And here we can also do the same analysis. So after projection, so the deviation from the constraint is actually much smaller than the one before doing the projection. Okay, and finally we will give some examples to explain the performance of the algorithm. Okay. And this is some general example with different potentials for the spin 1 case. And here is the normalized grain flow with our inexact projections. So the blue line is the residual of the Euler Lagrangian equation. So you will see it's always decreasing. So it means the algorithm is convergent. And this red one is the deviation from the total mass, and this green line is the area of the total magnetization. So from here we see initially you will see the constraints are not satisfied exactly because we use inexact projections. But soon you will see these two deviations is actually can be conserved in machinery accuracy. Okay. So that means the green flow process will automatically correct the solution onto the manifold. And here is the second projection. And here we compare two different inexact projections. So in these numerical experiments, we do not see too much difference between these two. And we will see, and this a comparison between this exact projection and this inexact projection one and the second inexact projection. And as we will see that in all examples, they all produce the same results and probably the same time cost. Okay. Because in the spinor one case, we also have explicit formula for the exact projection constants. Okay. And this for the spin 2. Spin 2 here, normally we need to solve an algebraic equation to get the projection constant for the exact one. And this, of course, will cost some additional time to solve the algebraic equation. But it's marginal. And for all the cases, we have the results are almost the same. And it seems that the projection does not affect too much of the iteration of the total iteration number. Okay, so this is the other case. We'll see for the spinor case. You will see for all the examples, we all have the same results. And of course, because the exact projection, we need to compute the projection constant, so will cost some extra time. But the projection does not affect too much of the total iteration numbers for the convergence. Okay, I think this is the final slide of my talk. So to conclude, here we introduce a normalized green flow approach to compute the ground states. In particular, the classical way to do it, you have to use a very special discretization to avoid artificial error in time step tau. And once we use this green flow plus some Lagrangian multiplier, then the discretization can be more flexible, and also the extension for the spinor case can be very straightforward. So this okay. So this some of the materials can be found in the papers here. Thank you for your attention.
Questions? Please.
You use conjugate gradient descent, yes?
It's not here. We can use conjugate gradient descent, but here is just the simplest steepest gradient descent.
Are you familiar with using Newton's method? How do you think the two? If so, would you how would you think the two would compare?
Newton's method, but I know in optimization we can approximate locally with a quadratic programming problem using Newton method to solve it. But for the grain flow, I'm not sure.
Okay, thank you.
Yongyon, what about generalizing for not just the ground state, but the first excited state, the second excited state?
Then that would be better to use the based on the Euler Lagrange equation to solve it as an eigenvalue problem, because this one we use the minimization characterization of the ground states. So for the first excited, if there are some symmetries, we can still compute. But above the first excited, then I think this grain flow type method is not easy to extend.
Thank you. So there is an optimization technique that is alternative to gradient flow that has recently received some attention in the optimization community, namely the Nesterov method. Do you know if this has ever been applied to compute the ground states?
You mean the second order acceleration technique?
Yeah, it's a kind of accelerated technique that starts with a gradient flow equation, which is second order in this pseudo time, and it has certain advantages over steepest descent, especially if the problem is poorly conditioned.
Yeah, I think there are some recent people trying to do this. Yeah. Let me check.
So that method has been known for 25 years since Nesterov invented it. In I think maybe more than. The answer is yes. Yeah. Okay.
Yes. I think recently there are some people trying to do this.
So a relatively stringent test of your methods would be phase transitions of the ground state. So in spinor systems, there is antiferromagnetic, ferromagnetic, easy plane, and easy axis, depending on the quadratic Zeeman and the spin-dependent part of the interaction. The question is, how would your method fare? How well would it do close to phase transitions between, say, easy plane and easy axis, like very close to the phase transitions? Would it be very accurate and how long would it take? I think that would be a very stringent test of the method.
I see. We haven't tested that yet because we haven't done the test for trying to figure out the phase transition diagram. But we are sure once converged, the solution is exact, so it's accurate. So I think we can test it in future.
Thank you.
Thank you.
Okay. Introducing Lagrange multiplier looks very nice to find the ground states. And I have one short question. So the explicit form of Lagrange multiplier depend on the scheme itself.
Here?
Scheme over here. Here. This is fixed?
Yes, because this one is determined from the continuous normalized grain flow. So this can be computed directly by the. So it's actually nothing but this actually just the chemical potential if you have this L2 norm equal to 1.
It looks that the constraint does not rigorously satisfied, right? Especially in the initial stage.
In the initial stage, you mean this is why initially is not equal to 0?
You constrain some normal or spin.
Oh, you mean the spinor? Yeah, yeah. For the inexact projections, so but the initial states we normally choose to satisfy the constraints, but for the first few for the projections, we do not ask the exact the satisfaction of the constraints.
Okay.
But if you evolve following the grain flow with Lagrange multiplier, so they will automatically come to be exact.
Okay. Okay. Okay.
Yeah.
Yeah.
But I mean numerically exact.
Yeah. 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 Okay.
Numerically exact.
Thank you.
Well, if there are no questions, thank the speaker again.
Thank
It was
you.
a nice talk.